as well in an earlier chapter. So I just want to kind of finish up some of these last examples here since we do have, I think, a holiday on Wednesday. So that way we won't be too far behind and stuff like that. So we were talking about really today sort of these intermolecular forces. And again, these are the forces that are responsible for boiling points, melting points. There's really three sort of big intermolecular forces that we talked about. Again, hydrogen bonding, which is sort of the strongest out of all of them. And it involves really polar molecules. And they're polar molecules that basically have a hydrogen that's directly bound to a nitrogen, oxygen, or fluorine. We also have dipole interactions, which is essentially also for polar molecules. The difference, though, is that these are polar molecules that really do not have the ability to hydrogen bond. So they don't have that ability to hydrogen bond. Still relatively strong force, not as strong as hydrogen bonding, but it is kind of the second strongest. But it's for polar molecules that have that ability to not have that ability to hydrogen bond. Lastly is dispersion forces, and dispersion forces are really for nonpolar molecules. Nonpolar molecules essentially means, as we talked about, that there is no separation of charge. So there's not a positive side, there's not a negative side, or anything like that. So they're sort of neutral, and they really rely upon sort of temporary attractive forces that occur. So that could be something like an instantaneous dipole, where basically the electrons decide all the kind of vacation on one side of the molecule versus the other, and creates this sort of temporary moment where that molecule that normally doesn't have a charge or separation of charge gains a separation of charge. And that gives them that sort of weakly way to interact with each other. And it's the weakest out of all of them. Again, the stronger the intermolecular force, the higher the boiling point and melting point will be. The weaker the intermolecular force, the lower the melting and boiling point will be. A reminder, as we saw with the last example, though, as we also spoke about, if you have something that is ionically bonded, that is really a intramolecular force, and intramolecular forces are always stronger than intermolecular forces. So that's why, again, on that one that was an ionic guy, we chose it as the highest because that is an extremely strong attractive force and is much stronger than hydrogen bonding, dipole, or dispersion forces. Any questions on any of that stuff there we've been talking about? So let's take a look at this one here. And again, if you're trying to decide something like this question here, which is the following would have the lowest boiling point, it's a good idea to try to identify what's happening in terms of the intermolecular forces, if that's what you're dealing with. If we just quickly scan all these guys here, they all are basically organic compounds, which are basically carbons attached to carbons and hydrogens attached to that. And a couple of things that you should know is, right, a carbon-carbon bond is definitely nonpolar. The carbon-hydrogen bond is also nonpolar. So pretty much all these guys here are going to be nonpolar molecules, which means that they are all going to be using dispersion forces as their main sort of intermolecular force. So the other thing that we talked about was, because these dispersion forces are really relying upon kind of those electrons moving one way or the other, the strength of a dispersion force actually increases with molecular mass. And that's because when we have more atoms, we have more electrons. More electrons gives it a greater chance of them moving around and kind of creating these temporary charges. And that's what we would want to kind of look at here. We obviously have 2 carbons on this guy. That's less than this guy, which has 3 carbons. So this guy probably should have a higher boiling point than the first guy. CH4 is 1 carbon, so that definitely is less than the first guy. So the C2 should actually have a higher boiling point. 5 carbons would be higher boiling point than the CH4. 4 carbons would be higher boiling point than the CH4. So even though they are all using dispersion forces, the CH4 technically should have the lowest boiling point because it has less atoms, less electrons, and a lower chance of those electrons moving around than something with the 2 carbons, 3 carbons, 4 carbons, 5 carbons. Out of all these, the guy with the 5 carbons probably would have the higher boiling point out of all of them. Again, it has more atoms, more electrons. greater the chance of those electrons moving around. That is what is sometimes referred to, if you take 1A, sometimes referred to as polarizability. So something that's easily polarizable is something that has a lot more electrons, and that's a fancy word for electrons being able to kind of move one area to the next. Any questions on that particular one? So let's take a look at this one here. We have CH4 and CCl4. We want to know, it's saying CH4 is a gas, while CCl4 is a liquid. What is the difference between them? So again, here we want to look at each of these and sort of identify what type of forces are involved. So CH4, as we've seen a couple of times already, again, all carbons and hydrogens, as we saw in the last example, is going to use dispersion forces here because it's nonpolar. CCl4, if you quickly jot a Lewis structure of CCl4, it looks something like this. And if you remember from Lewis structures, this is a symmetrical geometry. This is tetrahedral. Everything on the outside is the exact same element in that symmetrical geometry, which means this guy also would be a nonpolar molecule because of that. And because it's a nonpolar molecule, this guy also would be using dispersion forces. And because they are both using dispersion forces, what's going to make one a gas versus the other a liquid in this case is going to be the difference in molar mass here, right? This guy down here has a lot more molar mass, higher molar mass, more electrons. More electrons means it can actually do a greater dispersion force. Oh, greater is a better word, or higher. I guess greater is a better word, I guess. A greater dispersion force than our CH4. And because of that, we would expect our CCl4 to have a higher boiling point than our CH4, which should have a lower boiling point. So how does that translate into one being a gas and one being a liquid? Because our CH4 has a lower boiling point, it means it doesn't take as much energy for this guy to go into the gas phase, right? As opposed to our guy down here that has a higher boiling point, which means it takes more energy for it to go into the gas phase. And that's probably what explains why it is found as a liquid, why CH4 is found as a gas. Because CH4 has a weaker dispersion force, it's going to easily kind of go into the gas phase really quickly. The CCl4 has a stronger dispersion force, which means it's going to take a little bit more for it to kind of break apart and go into the gas phase. So it will stay, in this case, in the liquid phase. So in terms of our answers here, CCl4 is polar. That is not true, right? CCl4 and CH4 have different geometries. They don't. They both have tetrahedral geometries. That's not true. CH4 exhibits hydrogen bonding. It does not, as we talked about earlier, so that's not true. Cl is more electronegative than H, may be true. So really probably the best answer here would be none of them. What really, again, makes one a gas and one a liquid is what we were just talking about. Really that difference in molar mass. Again, the presence of more electrons is going to give CCl4 a stronger dispersion force than CH4, which would have a weaker dispersion force. And that's going to relate into a lower boiling point for CH4. Any questions on that? Okay. Which of the following would exhibit the strongest intermolecular force? So again, we just kind of want to go through and see what we got going on in terms of types of intermolecular force. So we've seen this guy a lot. He's going to be using dispersion forces. We've seen water a lot. It's going to use hydrogen bonding. N2 is a nonpolar molecule, which means it will also use dispersion forces. CO, even if you drew it, you're not sure what it looked like. It's basically a carbon and an oxygen. They are both in the same row on the periodic table, which means oxygen is more electronegative. It's probably going to be a polar molecule, and that means it would use dipole-dipole interaction. And helium, which is a noble gas, will use dispersion forces. So we know our order, right? The strongest is hydrogen bonding. second is dipole, and third is dispersion in terms of strength. So obviously this would not be the strongest. This guy right here would be the strongest, as this is dispersion forces, second strongest and weakest. So B here would be the correct answer. Any questions on how to kind of walk through that and determine that? Questions in general about intermolecular forces. Obviously, you need to be able to know what they are. You need to be able to identify a molecule, like these type of questions we've been doing, as to which one would have the strongest, the weakest, and obviously what that would relate to things like boiling point or melting point. Any questions on any of that part? Okay. So just to finish up, we're going to talk a little bit about vaporization and what happens. Vaporization, again, is that process when we do go from liquid to gas. As we talked about earlier, there is a certain amount of energy to do that phase change, take something from the liquid state to the gas state or backwards. And as we saw in that example earlier, that is our heat of vaporization. And again, that's the specific value there for water, which is the 40.6. Now, when something does go into the gas phase, it creates something that is known as vapor pressure. And when we have a sort of solution in a closed container like we have here, when we put that lid on it, basically what's going to happen is the rate of evaporation is going to increase. And we have this sort of process occurring at the surface of every liquid. There's a certain guys jumping out into the gas phase. There's some coming back into the liquid phase. So you have this at the surface of a liquid constantly occurring. Things going from the liquid phase into the gas and backwards from the gas back to the liquid. But when we first put the lid on it, the process of evaporation is going to increase. Obviously, with the lid on it, they have really nowhere to go. So at some point, you're starting to get some guys heading back the other way, coming back down into the solution. And at some point, what we would have is, by the way, that's the process of condensation, right? At some point, the rate of evaporation will equal the rate of condensation. And that is what is known as being at equilibrium at that point. So that is a container that reaches equilibrium. And typically what you'll see is you'll usually see that sort of liquid level kind of come down just a little bit, because once it reaches equilibrium, there's a certain amount of liquid that's going to be lost and have a certain amount of gas. Now, what does that have to do with vapor pressure? Well, there's always going to be a certain amount of gas molecules above the liquid. And since gas molecules create pressure, the greater the amount of gas molecules above the liquid, the greater the vapor pressure we would assume it to have. So the amount of vapor pressure is related to the amount of gas that's above a liquid in this particular case. And we typically won't have the entire volume evaporate off, right? And that's different than if you had this same sort of container and it was open, right? If this container was open, as this process of evaporation occurs, you give it a path to escape. And then there's air, right? Air will blow these guys away. And these guys that basically went into the gas phase are no longer available to come back down into the liquid phase. And eventually what will happen, right, with the liquid in an open container is the volume will get smaller, smaller, and eventually evaporate off because of that. Also, why, right, when we spill something just on like the bench, right, and it's spread out, it evaporates relatively quickly because we have that process of evaporation occurring on that spill. We have that air molecules that are pushing that gas water away, if you will, not available to come back into the liquid phase, and eventually our little spill kind of evaporates, away basically as that process. In addition, in sort of an open concept on the bench, we have evaporation happening everywhere, right? Greater surface area of that happening. So it's happening all over the place and then evaporates the kind of spill relatively quickly. Any questions on that there? So when we have a lot of pressure above a liquid when it's reached equilibrium. Again, that is what is known as something having very high vapor pressure. Things that are referred to as being volatile typically have high vapor pressure. They have high vapor pressure because they could go into the gas phase relatively easy. And they're able to go into the gas phase relatively easily. That means that they are going to create a lot of gas molecules above the liquid, and it's going to have a greater pressure at that point, or vapor pressure at that particular point. So when we think about our intermolecular forces that we've been talking about, and we think about, what would allow something to kind of go into the gas phase relatively easy, we would think about something that has a weak intermolecular force. So something that has a dispersion force as its intermolecular force means it's not held as tightly, so it's able to go into the gas phase easier. When it's able to go into the gas phase easier, it creates a lot more gases above the liquid, and it would create a higher vapor pressure because of that. Something that has a stronger intermolecular force will stay together longer, takes more energy to break it apart, and it would probably have less gas molecules that could get above the liquid, and it would have a lower vapor pressure because of that. So something that's really volatile, probably is held together by very weak intermolecular forces, allows it to escape the liquid, go into the gas phase very quickly, and we have a much higher vapor pressure because of it. Any questions on that? And that's what we see here again. Excuse me. So we have our differences in our vapor pressures at a given temperature. What helps us as well, if we increase the temperature as well, if you just think about it, if you increase the temperature, you're probably adding more energy. More energy is going to allow everybody to come apart into the gas phase, going to create more gases, and thus we would have a higher vapor pressure at that particular point. So again, obviously, if you increase the temperature, providing more energy, allowing things to get into the gas phase a lot easier, and thus would have a sort of higher vapor pressure. So as I mentioned before, molecules really with those weaker intermolecular forces typically will have lower boiling points. And again, lower boiling points translates into our higher vapor pressures because that is where that transition occurs. So that's why boiling points is important, because that is a transition where something goes from liquid to gas. So the lower the boiling point, the easier it's going to be to get into the gas phase. The more gas that you have, the greater pressure you're going to have in that particular situation. So when we think about temperature and sort of boiling point, the vapor pressure of a liquid is equal to the atmospheric pressure. And really, what happens when something boils, if you think about it, is you need to create a bunch of bubbles, right? Big bubbles. And inside that bubble, for example, let's say this is water. Inside that bubble is basically water in the gas phase, right? And those bubbles need to reach the surface. And if you ever boiled water before or seen it boiled before, you sometimes will see bubbles form and then kind of pop, right, before they get to the surface. And that's because what's happening in the solar open system is we have atmospheric pressure pushing back down on it. And in order for these bubbles really to kind of get to the surface and pop to release the gas that's inside, it needs to really reach a pressure that's equal to atmospheric pressure, sometimes maybe a little greater, equal to atmospheric pressure. And that's going to allow those bubbles really to get to the top and pop. And really, that's really when your solution's really boiling. If you ever heated water before, like you're making pasta or even with a Bunsen burner, you'll sometimes see once as soon as you hit the heat on it, you'll see a whole bunch of these little dots, like little bubbles kind of form. And the solution is really not boiling at that point. What you're actually seeing is the CO2 becoming less soluble in water because it quickly got heated. And that's actually what you're seeing with those little bubbles that kind of form really quick. It's not really till you get those kind of bigger bubbles, right, that really start to boil and work their way from the bottom to the top, that the solution really is sort of boiling at that point. And again, in order for those guys to make it to the top, they do have to have sort of a pressure that's sort of equal to atmospheric pressure to allow them to actually make it to the surface. That's why at lower atmospheric pressures, for example, in mountains, a liquid will boil at a lower temperature because its vapor pressure reaches a lower atmospheric pressure at a lower temperature, and stuff like that. Why you can boil an egg at 80 degrees Celsius maybe than 100 degrees Celsius and stuff like that. Any questions on things like that? So what is the vapor pressure of water at 100 degrees Celsius? So normal, like we talked about in gas, standard temperature and pressure is 1 atmosphere. 1 atmosphere is the same as 760 torr, and that is the same as 760 millimeters of mercury. These are all the same, right? And that would be the vapor pressure of water at 100 degrees Celsius, sort of at sea level. And all of the above here would be the correct answer in this particular case. And lastly here, which of the following would be expected to have the highest vapor pressure at room temperature? So take a second and think about what you got going on there. All right, so again, we might want to look at these things and try to determine sort of what is happening. So again, as we talked about, we're looking for the highest vapor pressure. So basically what that means is we have a liquid, we have a lot of gas molecules above the liquid. In order for those guys to gain a lot of gas molecules above the liquid, it needs to be relatively easy for them to sort of escape, right? That means we're looking for something that would probably have the lower boiling point, right? A lot less energy for those guys to go from liquid to gas. And we're looking for something with a low boiling point, means it should have a relatively weak intermolecular force. So again here, if we just get rid of like all this here, that's all carbons and hydrogens, that's all nonpolar. This part right here is kind of important. We have basically that bond there, and that is a hydrogen that is bound to an oxygen. That to me tells me it has the ability to hydrogen bond this guy, which means we should expect this guy to be relatively high in terms of boiling point. So that might not be the best choice. This guy as well, all that carbons and hydrogens, not really important, it's nonpolar, but we do have this group right here at the end, and that is a hydrogen that is bound to a nitrogen, which also means it has the ability to hydrogen bond. So this also will be relatively high in terms of its boiling point. So that might not be a good choice. This is all carbons and hydrogens, absolutely nothing else involved. Carbons and hydrogens, these are organic compounds. Carbons attached to carbons nonpolar, carbons attached to hydrogens nonpolar. This is a nonpolar molecule, which means it could use dispersion forces as its main intermolecular force. Same thing here. We got carbons and carbons, carbons and hydrogens, also nonpolar, going to use dispersion forces. So these last two here are the weakest out of all of these. These guys are the strongest. So since the first two are the strongest, that's not going to help us with higher vapor pressure, because the stronger the intermolecular force, the lower the vapor pressure will be. So those two are not going to be good for us. So we do have to choose between these two things. So we've seen this before. When we have dispersion forces and we're comparing a dispersion force to another dispersion force, dispersion force strength increases with molecular mass. So C has a lot more atoms involved than D. So C should have a higher molar mass. Higher molar mass should be more atoms. More atoms should be more electrons, greater opportunity for it to do dispersion forces. So D actually here should be our answer. D is using dispersion forces, but has a lower molar mass, which means its dispersion force is going to be weaker. Because it's weaker, it should have the lowest boiling point. Lowest boiling point means it's going to be able to go into the gas phase a lot easier than the other three. And because it could go into the gas phase a lot easier than the other three, it should then create a lot more gases than the other three above the liquid. A lot more gases above the liquid should result in a higher vapor pressure. Any questions on any of that there? All right. Any questions on intermolecular forces, any of those type of things? All right. Then we have types of solids, which is next. And, and I'm not really feeling solid. So we'll look at this. We officially lectured on it. This is crystalline solids. There's ionic solids, molecular solids, and atomic solids. I feel really good about solids. You don't have to worry about solids for us. So this section you don't have to worry about. So it looks like it's 14.5. You don't have to worry about it for us in here. That should wrap chapter 14. Any questions on that there? Okay. So that is the last chapter is going to be on our exam, which is coming up. Again, we have a holiday on Wednesday, right? Just Wednesday, there's no class. I believe it's Veterans Day. So we have that off. And when we come back on Monday, we will have the exam that will cover through chapter 14. Let's see here. It is chapters 6, 7, 9, 13, and 14. Trying to remember, but I think we got some balancing equations, types of reactions. So balancing equations, types of reactions. We also should have some stoichiometry involved in there. We also should have gases, and we should have pretty much our intermolecular forces along with our sort of heat of fusion, heat of vaporization, specific heat. Any question on what's going to be on the exam? Again, the solids you don't have to worry about in chapter 14. Any questions on that? Yeah, there will be a review module up there. I'll put it up there. I thought I clicked it. I might have clicked it off by accident. I'll be up there as soon as class is done today. I'll pop it back up there for you. Other questions on that for practice stuff? I'll throw it right around whatever week we're on, right around week 14. I'll put it right there. That way you can find it. Other questions on that? I think I did move the homework for Cengage, so that has been moved. So again, that will be due on next Monday. So we'll do what we normally have been doing is we'll have a short little lecture just to kind of keep on pace. We'll take the exam during lab time. And again, I think it's basically some balancing equations, types of reactions, stoichiometry, gases, and this stuff